In this Brooklyn laboratory, a thirsty rat can get water on its own just by thinking about it. No more need for levers. Electrodes send signals directly to the machine. The head of this lab, where rats can control machines from afar, is John Chapin, a pioneer in neurorobotics. He's developing what are called brain-machine interfaces, a technology that marks the beginnings of a new kind of man, the cyborg, the robot man. But as usual, before there is a man, there is a rat. In this case, the robot rat. A remote-controlled rat. Neurorobotic technology can be applied in different directions. The brain controlling the machine, or, inversely, the machine controlling the brain.
So we're just going to go through each one of these arms. 1, 2, 3, 4, 5, 6. Let's do all of those, and he'll just do it.
But a third option is also possible. One brain controlling another brain via the interface. How does this work in the case of the robot rat? All you need, in fact, are 3 well-positioned electrodes. Two electrodes in the sensory cortex of the rat send stimuli to the zones connected to its whiskers. When the rat follows the signal sent to its left side and turns in that direction, it is rewarded with a discharge into its pleasure zone. This discharge produces a flow of dopamine, providing instant pleasure. This zone is also called the brain's reward center.
The feeling of touch really comes from a stimulus inside the brain, so it's a virtual touch stimulus. Now this rat has spent its entire life in a cage, and probably isn't going to want to walk down this very, very steep ladder, but we're going to motivate it so that it tries to go ahead and do it.
We possess a reward center too, just like the rat, as well as a sensory cortex and a motor cortex.
Here is the sensory part of my leg. Here is the sensory part of my hand. Here is the sensory part of my face. So there's a whole strip of sensation going from my face all the way down to my legs. Similarly, just a little bit in front of that, there's another strip, and that's the motor side. So this would be movement of my face, this would be movement of my hand, and this would be movement of my leg.
In the process of creating a cyborg, this is square one. If we send a stimulus to the zone related to the hand, we create a sensation in that area. In the same way, via the motor cortex, we can provoke an involuntary movement.
Originally, we did this because we were interested in people who have spinal cord injury. We could put an electrode inside the brain area that when we stimulate it, it makes it feel like you're being touched on your hand. And so if we had a robot arm, or if we even had little sensors on the hand, when we touch something, when we would actually be able to feel it. So now that we've shown in rats that it's possible to stimulate in the brain and produce tactile stimuli, we are doing this in monkeys now. And of course, to go to the next level and do it in humans means that we have to do several years of studies in monkeys to show that it's safe, to show that it can be done.
On the promising front of neurorobotics, other researchers have already crossed the line and passed from animal model to humans. In Boston, the first machine-brain interface trials have already been conducted on paraplegic patients. Thanks to an electrode chip called the BrainGate, they can operate a computer remotely by thought. No more need for a voice recognition system.
I'm going to open the first email, which says congrats. It says you are doing a great job. Next, I'm going to open the second email, which states hi there. It says hi, we'll talk soon. Now I'm going to the exit. Next, I'm going to paint a circle. That's the best circle I can do. Now I'm going to exit.
Today, paraplegics are the only voluntary guinea pigs willing to test these highly experimental machine-brain interfaces. They are the ethical, acceptable gateway for neurorobotics, and many civilian and military applications are already being imagined.
Now close it?
Now close. Nice. Open. Close. Not bad, man. Not bad at all.
For the human work, it's essentially is shown possible to move a cursor across a computer screen. And what we want to do is to have the human brain essentially move a robot arm. It was an interesting situation where a completely different area of science was produced, where we were trying to produce a neuroprosthesis, and here we came out with a guided rodent.
Such is science. The possible applications are always greater and more worrisome than the good intentions of the start. So it's no coincidence that these researches are partly funded by DARPA, the U.S.'s defense research agency. Neuroscience will bring us the soldier of the future.
This is a new deal, gentlemen.
Enemy center of gravity is downtown. Should get a good view from here.
A remote-controlled soldier? A soldier who in the midst of a battle can be sent crucial data and information downloaded into his brain? A soldier who can control his fears and command firepower by thought? At this stage, anything is possible. It is just a question of time, investment, and priorities. The 21st century has ignited under the sign of the cyborg. We are going to reach a level of control that still seems like a fantasy to us today. And yet, the great social and philosophical issues of tomorrow are first tested and raised here in the brain research laboratories and their favorite animal model, the rat. The more we learn about the brain, the more researchers discover how little our consciousness and will control our choices and behaviors. Our way of living might be completely transformed by the convergence of neuroscience, genetics, and nanotechnology.